My name is Noah Nelson. I am a student at BYU in Physics 106, and my professor is Dr. Delacourt. And today I will be talking about converging and diverging lenses. If we look over here in the top left of the screen, we can see the shape of a converging lens and a diverging lens. Another name for a converging lens is convex, while another name for a diverging lens is concave. Another distinction, converging lenses always have a focal length which is positive, whereas diverging lenses always have a focal length which is negative. There's three equations, if we look over here on the left of the screen, three equations that we will be using with our lenses. 1 divided by the object distance plus 1 divided by the image distance equals 1 divided by the focal length. The F stands for focal length, and it's the distance between the focal point and the center of the lens. If you look over here at case 1, we can see that the focal length would be between the focal point, this red dot, and the center. So if we draw that, focal length would be this part right here. The object distance, DO, distance between the object and the center of the lens, and it will always be positive by definition. So if we look back at the picture over here, the object distance is going to be between this arrow, which is our object, and the center of the lens. So that would be all of that. That would be our object distance. The image distance is the distance between the image and the center of the lens. So this object is going to go through this lens and create an image. We will get to where the image is formed, but what we need to know is if it's positive, then the image is going to be real, while if it is negative, the image will just be a virtual image. Moving on to the second equation, we have magnification equals the image height divided by the object height, or it equals negative the image distance divided by the object distance. Magnification, and some important things to know about m. If the absolute value of m is larger than 1, then the image is going to look enlarged compared to the object, whereas if the absolute value of m is less than 1, the image is going to look reduced relative to the object. Another important thing is the sign of m. If it is positive, then it's going to have the same orientation as the object, whereas if it is negative, it'll be opposite orientation as the object. The last equation, P equals 1 divided by F. P stands for the power of the lens, and it is measured in diopters, or a big D. 1 divided by the focal length will give us the power of the lens. If we look over here, there on the top right of the screen, there's 3 different cases which are important to know and which will cover any lens. So in any lens problem, there's only 3 cases that could happen. In case number 1, we have a focal length which is positive. So if you remember from what I said at the beginning, if the focal length is positive, that means it has to be a converging lens. So we have a converging lens, and the object is greater than the focal length. So over here in case 1, the object is farther away than the focal length, which is right here. In case number 2, we have the same thing. It's a positive focal length, so it's going to be a converging lens, but this time the object is less than the focal length. So as you can see in case number 2, the object, which is this arrow, is inside of the focal length because it is shorter. And in case number 3, we have a negative focal length. As you can see in case number 3, now we're using a diverging lens because the focal length is negative. And an important distinction is it doesn't matter if this object is less than the focal length or greater than the focal length, the results will be the same. Whereas in a converging lens, it does matter. Okay, so let's start with case number 1. So we know that this red line is our focal length, and we know that the blue line is our object distance. And what we're going to want to find is what our image distance will be. So to do this, we need to draw a ray diagram. And to draw a ray diagram, we need to realize that a converging lens is going to converge all the rays towards this focal point after the lens, whereas a diverging lens is going to diverge the lenses away relative to this focal point. So we'll get to that once we get to case 3. But so for case 1, we are going to draw our first line, which is just going to be parallel until it hits the lens. And when it hits the lens, it's going to converge onto the focal point. So come down through the focal point. And that's our first line, or our first ray. Our second ray, we will just go straight through the middle of the lens, and it just goes straight all the way through. Our third line, we're going to draw through our closer focal point, and then once it hits the lens, it's going to be the same angle as up here, so we're going to have to draw it going parallel. And you can see where they all meet right here is where the new image is going to be. So if I go ahead and draw this new image, it would look like this. So here's our image, and the image distance would be this distance right here. So some important things to know about this case. So the image distance is positive, which means that the image type is real. And also the magnification of the image is negative. So that means, if you remember, a negative magnification equals opposite orientation as the object. So that's why the arrow is down here and it looks opposite of the object. Next thing we got to do is look at case number 2. So in this case, we have our object in front of our focal point. So the ray diagram is going to look a little bit different this time, even though we're still using a converging lens. So for the first ray, we're just going to draw it parallel again. And it follows the same principle. It just goes straight through the next focal point. The second ray, we have to draw relative to this focal point. So if we take this line straight up, go up here, and then straight out parallel. Now with the last ray, we have to just draw it going straight through, just like last time, straight through the lens. And now you might be wondering, where do all of these 3 lines cross? Well, in order to find that out, you actually have to extend the lines backwards. And when you extend them backwards, I like to use a dashed line so that I know that this isn't actually where the light is. It's just a virtual image of the light. And so they would all cross somewhere over here. So let's draw in our image that it would create. That's right here. So we have our image, which is actually behind of our object this time, and on the same side. So that means that our image distance right here is negative. Negative means that the image distance is on the left, whereas up top it was positive, which means it's on the right of the lens. So because it is negative, we know that it is a virtual image. And the last thing to note is that the magnification is greater than 1, which means it's enlarged. So as you can see, it is bigger than the object. Okay, so the last case that we need to look at is case number 3. And case number 3 is it doesn't matter where the object is, it can be either in front or behind the focal point, but the focal length is negative, so we're using a diverging lens. Now to draw this ray diagram, we need to realize that the rays are going to diverge instead away from this focal point relative to this one, instead of converging towards it like last time. So in order to see this, let's draw ray diagrams. So we'll draw our first line going parallel again, and then what happens is it diverges. So if you look at this focal point over here and just imagine a line going straight up, continue that line onward, and the ray would look like that. With the next line, if we just go straight through it, we can draw our line going all the way through. And then with the last line, what we're going to have to do is do a line from the object to this last focal point. We come across, and what's going to happen is it's going to go parallel. So how you can find where all these lines meet is you have to use the dashed lines again. And if we take all these lines back, the image is going to be right here. So it's kind of hard to see, but if we try to draw in our little image of our arrow, it's going to be something like that right there. And so some important things to know about this case is if we look at the image distance, it's on the left side again. So the image distance is negative, and because it's on the left and because it's negative, it's a virtual image. So this image right here is virtual, and the magnification is less than 1. So when it's less than 1, the image is going to look reduced relative to the object. And it doesn't matter, even if our object was over here, it would still be somewhere over to the right of it, and it would be reduced in no matter what. That's for case number 3. The thing I have today about converging and diverging lenses, if you would like practice on these equations, I would suggest replacing some of these variables with made-up numbers that you have, and then seeing how changing the numbers would change some of the variables. So I would mess around with these equations and try to put in different numbers and see how that worked. I'd also practice doing these ray diagrams because I know it can be confusing. But just remember that there's always 3. They always use both focal points, and one always just goes through the center of the lens. Thank you very much.